SwayamPrabha. Digital India. Educated India.
The content outline of this lecture is as follows. First, the objective and course content, the direct problem, the inverse problem. How do you describe the error statistically, non-linearly squares, and Bayesian inference? Of course, this lecture is only about my portions. Of course, I added one or two slides, maybe one slide on S. Balaji's portions also. So what is the objective of the course? As stated in our Senate, this thing as stated in our ordinance, whatever, BTech regulations, to give the students an overview of inverse problems in heat transfer and ways of formulating and solving them through examples. I come again, to give the students an overview of what inverse problems are all about in the field of heat transfer and what are the ways of formulating and solving them through examples. Now somebody can switch on the mic and tell me how much of these objectives are fulfilled. Did we do justice? So just tell me. Course content. First we did introduction, examples of inverse problems in heat transfer, famous missile re-entry problem. Some food is getting stuck. There's a problem with eating bread in the morning. Huh? Some that crumbs will get stuck somewhere when you start speaking. They will. Rice or chapati will not give the problem. Examples of inverse problems in heat transfer. Definitions, difficulties associated with the inverse problem, ill-posed problems, and nomenclature. Then statistical description of errors. Then solving an inverse problem is an optimization problem, parameter estimation and function estimation, classical techniques, calculation of sensitivity coefficient, the Liebenberg-Marquardt method, Tikhonov method, regularization. Alifonov, I just told you briefly. That is how to get the lambda parameter of the Tikhonov dynamically. Examples from conduction, convection, radiation, heat transfer, MCMC, Markov chain Monte Carlo methods, Bayesian framework, likelihood density function, posterior probability density function, priors, point estimates, expectation, maximum a posteriori, and standard deviation of estimate. Not bad. Today, last class also 50 people are there, nearly 47. 47 are there, two or three are me and the TA, so 45 out of 100. That's not bad. MH algorithm, Gibbs sampling, of course, I didn't teach you because we didn't have time. We taught you only the MHMC, MCMC. The Gibbs sampling, what we do is just a 30-second introduction. Instead, they accept the new sample is continuously accepted. So the Gibbs sample is slightly inferior, but there is some funda in that. So there is a new sample generated, is continuously accepted, and that the generation of the new sample has got some fundas. So that is the Gibbs sampling. Instead of using a acceptance function, 3 random numbers, that is the MCMC, right? Okay, that is the Metropolis Hastings. Computational implementation of MH. Priors, what is the use of priors? Hierarchical priors is something which I did not tell you, but I briefly told you. Even if you don't have the mu and sigma of the prior, you can assume a Gaussian prior and treat the mean and sigma of the prior also as unknowns and pull them out, retrieve them also. This is called a hierarchical prior. Okay, and then that information is a jettison. I mean, you don't use that. So that means if you have one parameter unknown, thermal conductivity, the unknown will be, so finally the output will be your PPDF for the thermal conductivity. You will also have a PPDF for the mu of the prior and sigma of the prior. So you will get 3 outputs, though you want only thermal conductivity. But what you are assuming is that the prior is a Gaussian, whose 2 attributes, okay, whose 2 parameters, whose 2 constituting parameters mu and sigma are unknown. Examples in heat transfer, surrogate models, deep learning, ANN, CNN, RNN, PIN, hybrid estimation techniques. So I think Professor S. Balaji must at least briefly explain to you how you can use a hybrid estimation by combining deep learning with Bayesian and deep learning with GA. Okay. Examples in conduction, convection, and radiation. Deep learning is basically you have more than one hidden layer. Okay. And then what you can do is, if somebody has already learned GA, genetic algorithm, then instead of solving analytically the optimization problem, you can use a GA. For driving the GA, you can use the neural network model. An inverse problem is one in which the effects are estimated predicted from causes. It occurs in all branches of science and engineering. The easier problem to solve is X going to Y, cause going to effect. You're vaccinated, 1 or 2 days, you have fever. That is fine. There is a forward problem. But I have fever. What is the effect? So I'm sorry. So the effect and cause, that terminology must be interchanged. The effect is the fever, then the cause could be anything from COVID-19 to cancer. Okay. So the inverse problem is harder to solve. Sometimes the available data is too sparse to sift through multiple causes. There can be multiple causes that could have caused the effect. That's what is happening right now. Inverse problems are quite recent and less than 4 decades old. Scientists from different fields are interested in the subject, but different goals and objectives. A mathematician looks at inverse problem with a view to develop new techniques to solve inverse problem. He's interested only in the method, technique, algorithm. This is the mathematician. An astrophysicist wants to predict the constituents of the atmosphere of another planet, say from its emission spectrum, absorption spectrum, something. He is taking a telescope, he's taking a spectrometer, something he is doing. Okay. And then he has a model, he's combining this to understand the atmosphere of other planets, stars, and so on. A statistician, quite different from a mathematician, is developing Gibbs sampling. He wants to develop Gibbs sampling. He wants to develop Metropolis Hastings algorithm, Markov chain, Monte Carlo, how to generate samples, importance sampling, heavy tail distribution. For example, 1 in a 100-year event like this, okay, the pandemic or something, extreme events. Can you predict extreme events as an inverse problem? So statisticians looking at distributions, parameters of the distribution, sampling algorithms, all this. So he or she wants to develop statistical techniques to solve inverse problems. For conditioning the PPDF, he wants to use a prior, what prior will use, whether you'll use a loose prior, you'll use a tight prior, informative prior, non-informative prior. What happens if, hello? Okay, quantification of prior information to improve the estimation. Okay, the flow chart is simple. At the left northwest corner of the slide, there is a certain set of measurements. Then there is a forward model. The forward model, you give the causes, it produces the effect. Effect is usually temperature or heat flux. Compare the measurement and model. This R square minimization is one such approach. Instead of R square minimization, you can also have e to the power of minus blah blah whatever. Generate a probability. That's what we do in Bayesian. Simple least square estimation will be if is the R square less than your epsilon. If it is yes, please stop the whole work. If it is no, go to an inverse model. What is the inverse model? The inverse model is basically either dou S by dou A equal to 0, dou S by dou B equal to 0. That is straight inverse model. Or the inverse model could be generation of samples, generation of then working out the PPDF. That is the Bayesian approach. So therefore, look at the left-hand side. 3 important constituents are there in the inverse problem. There is a measurement, there is a forward model, there is an inverse model. In the inverse model, if you quantify your beliefs, that is, you're a Bayesian, then your prior knowledge also comes into the picture. Therefore, it is not just modeling, it is not just measurement, it is not just an inverse model, it is also an incorporation of beliefs. Everything is put in a scientific framework. That is how we solve an inverse problem. Okay, what are the applications of inverse problem in thermal sciences and heat transfer? You want to estimate thermophysical properties. We have done this. K, okay, K is 1, Cp is 1, alpha is 1. That is, these are the various parameters you want, various quantities you want to retrieve. Estimation of boundary heat flux. We have seen in some simple problem. There is a slab Q at the boundary you want to estimate. Estimation of spatially varying heat transfer coefficient. This is a research problem. Estimation of contact conductance. When 2 metals are joined and there is an imperfect thermal contact, there is a resistance. 1 over resistance is called conductance. This conductance obviously should be a function of the roughness, temperature, pressure, and so on. Just now I evaluated a PhD thesis from IIT Roorkee. So I just sent the report 4-5 days back. The whole 200-page thesis was on estimation of contact conductance in high vacuum conditions. Aluminium to aluminium, copper to aluminium, so various. And then he has put a thermal, the student has put a thermal grease, with the thermal grease, without the thermal grease. And then he has characterized it on 200 pages, heavy work. Last 5-6 years he has done this work. That's how you get a PhD, right? Then estimation of bulk radiation properties, absorptivity coefficient, emissivity coefficient, scattering parameters in radiative problems, radiative transfer problems. The accuracy of the inverse solution is a strong function of errors involved in the measurements. Measurement errors have to be statistically described. Okay, that's very important. First, the errors are additive. Measured error equal to actual plus error. This error could be the error in your instruments. The temperature errors have a zero mean. That is expectation of epsilon I, where epsilon I is the error is zero. The errors of constant variance. If the variance is different, you have a weighted least square. I'm talking now about least square method, plain least square, or OLS, ordinary least square. Errors associated with different measurements are uncorrelated. That means I can't predict the error in the third thermocouple by knowing the error in the first thermocouple. That means there is a bias. All the errors are correlated. Now you're considering exactly the opposite case. They're uncorrelated. The measurement errors follow a Gaussian. Okay, f of the error is 1 by root of 2 pi sigma square e to the power of minus epsilon square by 2 pi sigma square. Is that okay? Statistical parameters describing the errors are known, such as sigma. Standard deviation of the instrument is known. Only variables that contain random errors are the measured temperatures. All the other quantities, the location or the time in which you measure the temperatures are supposed to be known without any error. All the other quantities appearing in the formulation of the inverse problem are accurately known. If it is a non-Bayesian approach, prior information is not available. All right. What are the different key differences between well-posed and ill-posed problems? According to Hadamard, 1923, a well-posed problem, I think there's English problem there. A well-posed problem is one that satisfies. So much problem. Okay, a well-posed problem satisfies the following three conditions. The solution must exist, the solution must be unique, and the solution must exist, solution must be unique, solution must be stable under small change to the input data. All forward problems are well-posed problems, but the inverse problem, one is fine. Often the solution exists. Solution is unique also, we can prove for many conditions. But for an inverse problem in heat transfer, I'm saying, generally for an inverse problem, 1 and 2 are okay. 3 is always the sore thumb because small changes in input can cause large changes in the output. That is just called the sore thumb. So there is a difficulty. Then we have to discuss about statistical concepts. What is a random variable? A variable whose value is an outcome of a random phenomena. Tossing of a coin, whether heads or tail, that is a random variable, whether you get head or tail. Random phenomena is a tossing. A phenomenon is not random if the individual outcomes are unpredictable, although a regular pattern may emerge. So it's unbiased coin 100 times if you toss it 50 times, approximately 49, 51, 51, 49 or 50, 50 you will get heads and tail. Discrete random variable is something which can assume discrete values. Tossing of a coin, only two possibilities are there. It cannot be like a Sholay movie, right, where if the coin stands, it's neither here or there, okay? All right. Continuous random variable is one which can assume all values in the interval, so of real number, okay? The probability distribution, the assignment of probabilities to the values of random variable gives the probability distribution. The probability distribution is f of x, random variable is x. Fx is a non-negative function which has the property sigma n equal to 1 to n, f of x n equal to 1 and x is discrete. Integral minus infinity to plus infinity f of x dx equal to 1 when x is continuous. The expected value of random variable is basically the mean. So it is basically integral x of x dx when x is continuous. Sigma n equal to 1 to n, x of n, f of x n when x is discrete. What is expectation? Expectation, the expected value is the mean value. Okay. If there are 10 values, if you divide it by 10, usually in that case, x1, x2, x3 are discrete. So the E of x is basically arithmetic mean, which is basically simple to calculate. Okay, that's what I wrote. If f of x equal to 1 by n, E of x is the arithmetic mean of x. Expected value of a function of x, g of x, will be sigma g of x into f of x when x is discrete. The sigma will be replaced by an integral minus into plus into g of x f of x dx when x is continuous. The variance is basically the expectation of x minus mu whole square, where mu is the mean. Okay, so for example, heights of 60 students in the class, you can get the mean. Then height of first student minus mean whole square, height of second student minus mean whole square, add all the 60. Okay, divided by 60. So that will be the sigma square. Root of that will be the standard deviation. Alternatively, Sigma square is also the expectation of x square minus mu square. That I think I have proved, or you can prove. Covariance of two random variables is a measure of the cross correlation or a linear dependence between them. Generally, independent variables should have a covariance of 0. Otherwise, they are not truly independent variables. Covariance of xy is expectation of x minus mu x into y minus mu y. The covariance of xy should be 0 if xy are independent. This is okay. 0 if xy are independent. Normal distribution. Look at this. So if you add it has got a bell-shaped curve. If you add the orange or the light pink plus blue plus green, that is mu plus or minus 3 sigma. About 99% of the curve is obtained. How is that curve obtained? F of x equal to 1 by root 2 pi sigma square, all that. That is the ordinate. The abscissa is the random variable x, and then at the center x equal to mu. Okay. Then the probability of finding the probability of some random variable x lying between x1 to x2, two limits, is given by that minus infinity to integral minus infinity to x2 minus integral minus infinity to x1. Is it okay? Maximum likelihood estimate. Let us assume that all measurements are made with the same instrument and the measurements errors follow Gaussian with a standard deviation of sigma. Suppose you want to fit a straight line, f of x equal to ax plus b. The probability of getting y is given by the conditional probability is p of yi to get the temperature Ti for a given a and b is given by the distribution for given by the normal distribution function. The probability of getting all the points, that is T1, T2, T3, T4, or y1, y2, y3, y4 is the product of all the probabilities L. So that is a conditional probability of getting simultaneously y1, y2, y3, yn for a given AB. That is equal to the product of all this. Then you can sum up all the e to the power of minus, and then you can take z equal to minus 2 ln L. And then if you take dou z by dou equal to 0, dou z by dou b equal to 0, it will again lead you to the same set of equations which you obtain by simple least square. So what you obtain by simple least squares for a straight line is nothing but the maximum likelihood estimate. So what do you mean by the maximum likelihood estimate? The probability of the joint probability density of getting all the points for the assumed values of A and B, wherever it is maximum, the corresponding A and B, which are basically estimates. The corresponding estimates of A and B are the most likely candidates which cause these probabilities or which cause these temperatures. Okay. Linear least square in two variables. Let us consider y equal to f of x1, x2. The simplest case, y equal to a plus b x1 plus c x2. To estimate a, b, c, take the sum of the squares of the residuals. Y minus y fit whole square, sigma I equal to, so it's not 0, sorry, it should be 1 to n. Dou s by dou equal to 0, dou s by dou b equal to 0, dou s by dou c equal to 0. Three equations, three unknowns, you can find a, b, c. What is the motivation for getting this? Take a heat transfer correlation. The Nusselt number, that is a dimensionless heat transfer coefficient, is A Reynolds number to the power of m, Prandtl number to the power of n. Take ln both sides. Ln of nu is ln of A plus m ln Re plus m ln Pr. Therefore, look at the third line of the same U graph of this slide and look at the last line. Y now is ln nu, A equal to ln A, B equal to m, x1 equal to ln Re, C equal to n, x2 is equal to ln Pr. Therefore, it is not out of academic interest. Linear least square in two variables or three variables is very much used in heat transfer correlations where you get what is called power law form. What is a power law form? Nusselt number, where he says sum a1 to the x1 to the power of b, x2 to the power of b. x1, x2 could be Reynolds number, Prandtl number, aspect ratio, whatever, viscosity correction, all these things. Okay. All right. So you can do a lot of experiments for various values of Reynolds number and Prandtl number. Get the heat transfer rate, divide it by A delta T, get the heat transfer coefficient, convert it to Nusselt number, and then do a Excel or you could do a regression and get a correlation. What is the idea of getting a correlation? Somebody who wants to get the result from Nusselt number doesn't have to do all the hard work. What is hard work? You did experiments, then you regressed it and gave a correlation. This correlation can be used by others, okay, so that they don't have to go through this trouble and they can easily get the Nusselt number From Nusselt number, they'll get the H. From the H, they'll get the Q. Getting Q is the fundamental problem of convective heat transfer. Okay. Polynomial regression. Consider T equal to A plus BF plus CX square. This is frequently encountered in steady state conduction problems. We have already seen that if the thermal conductivity is a linear function of temperature or X or whatever, you'll finally get a quadratic form for T. Minimize Y minus Y fit whole square. Dou S by dou equal to 0, dou S by dou B equal to 0, dou S by dou C equal to 0. There are three unknowns in the three equations and three unknowns A, B, C. Please note that we have a tabular column of T at various values of X. The functional form of T equal to A plus BS plus CX square. So this is called a function estimation. Okay, you are doing a function estimation, and then you may do dou T by dou X at equal to 0, X equal to 0, multiply by K, get the heat flux. You can calculate the heat flux also. This is called a function estimation. Whereas from the linear temperature profile, if you just calculate the thermal conductivity, that is called a property estimation. So you can have a property estimation, function estimation, boundary condition estimation, and so on. Weighted least square. So let us say again y equal to ax plus b, but we are saying that every fellow ith reading has a different sigma I. Therefore, 1 by sigma I square, I call it as weight of I, Wi. Then you can do this. I think I gave it as an assignment test, correct? Was this given as a problem in the assignment test? Can anybody confirm?
Yes, sir.
Very good. Okay. Okay. You get all this complicated expression, sigma, Wi, sigma, x, all that. You have figured out all this. So this is Ws, weighted least square. The first thing we studied was OLS, ordinary least square. Non-linear least square. Consider the form y equal to a to the power of 1 minus e to the power of minus bt. This is a heating of a first order system. I told you examples where this is even simple immersion heater. There's an aluminum bucket, fill up water, put an electric heater and wait for it to get hot, heat it up so that you can take bath. You can take your snan. That follows this distribution. Now, A and B are unknowns. Whatever you do, ln of this thing minus 1 plus 1, 1 by y, it doesn't work. It has to be put in a nonlinear form. If it is nonlinear, what it means, even to start the iteration, you require some guess values of A and B. So what you have to do is, you cannot solve for A and B as such. You start with a value of A and B and get delta A and delta B for the next iteration. Then A plus delta A, B plus delta B is the A nu and B nu. From that you get A3, B3. Then go to A4, B4, A5, B5. Okay. So proceed. So what you can do is f of x of I, the j plus 1th iteration equal to f of x of I, j plus blah, 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 all that. And then we stop with first order terms, take the difference between these two. And now you can put it as a linear least squares in not A and B, but in delta A and delta B. So minimize the least square. So you will get this Z transpose T, Z operating on delta A equal to Z transpose T operating on D. So all this we have seen. I think so. We explained this. We have already seen example. Stopping condition can be AJ plus 1 minus AJ by modulus AJ into 100 less than epsilon. This could be used for D also. All right. So the GNA, the Gauss-Newton algorithm, is an iterative process. Successful solutions critically depend on the initial guess. Okay. So since it doesn't use second order terms, there is a chance that the algorithm can falter all along the way. Okay. So if the initial guess is wrong, as we have seen, it can be, the solution can cup. Also, the first derivatives are all violently changing the sign and so on. Then also, even then, there could be a problem. The improvements to GA, some conditioning is required. So Z transpose T Z plus lambda of identity matrix operating on delta is right side is the same. This was the modification proposed by Marquardt. Liebenberg said that. Liebenberg and Marquardt together is called as the Liebenberg together said that instead of taking lambda of identity matrix, lambda of the diagonal of Z transpose T Z operating on this. So one thing is you can start with first iteration of GNA, then switch to Marquardt or Liebenberg-Marquardt in the second, or first iteration itself, you can start with GNA. Whatever it is, GNA, MA, LMA, you need initial guesses to proceed. Okay. Lambda is a non-negative damping factor and can be altered. Choice of lambda comes from experience. LMA can work very well even if it starts off on the minimum, but of course far away from the minimum. LMA is more robust, even then it has its own limitation. The problem is all these methods find only a global minimum. So if there is a zigzag variation of y with respect to x, there are several local minima. Depending on where you start, you may get stuck in a local minima. Therefore, global algorithms like genetic algorithm may perform better. Then what you do is you start with a global algorithm like GA or something, and then once you narrow down to a particular region of interest, then fire that. Then fire your search by using your LMA or something. Okay. Tikhonov also has proposed a conditioning for nonlinear problems. So what he said that instead of minimizing Z S equal to sigma I equal to 1 R square, I'm going to the third line, third bullet, plus lambda of L square. He said that lambda of L square can be, if there are two constants A and B in a problem, it's lambda of A square plus B square. So he said that there is a penalty for high values of A and B. We don't know how it works, but it works. There is a mathematical proof for this also. I think this is also shared with you. Lambda is again something which you have to take. What Alifano has done is he will use a gradient search to optimally get the values of lambda 2 from lambda 1, lambda 3. He will dynamically adjust the lambda. So that is what Alifano has done. All these Alifano, Tikhonov, all these are Russian scientists. Okay. All right. Now coming to the Bayesian method. The Bayesian inference is a method based on the Bayes theorem on conditional probabilities. The probability of getting X for a given Y is the probability of Y getting Y for a given X multiplied by any prior knowledge you already have about X divided by P of Y. P of Y is the normalizing constant. So P of X is our belief, or the quantification of beliefs. It's called the prior knowledge. P of X given Y, the left hand side is called PPDF. PPDF, posterior probability density function. The P of Y given X is called the likelihood density function, and which is basically takes care of that is e to the power of minus whatever, my e to the power of minus sigma e to the power of minus s, okay, by 2 sigma square, whatever. So P of Y given X is the likelihood that takes care of both the forward model and the measurements. P of X takes care of the beliefs. Therefore, this Bayesian is a very good package, complete package, which involves quantification of beliefs, a mathematical model, as well as the measurements. Okay. So Bayesian does not tell you that this is the answer to the problem. It says that any X can cause that Y, but if the P of X of given Y is very less, that X is the unlikely cause for the Y. So wherever the P of X of Y is the maximum, that is called the maximum A posteriori. If you get the expected value, so if you get the expectation of the mean of the PPDF, that is the posterior probability density function, then it means that is a mean which can be expected. That is the expected value of X, which gave rise to this Y. What are these Y's? It could be Y1 to 5, Y1 to 100, Y1 to 1000 temperatures, heat fluxes in heat transfer, concentration in mass transfer, voltage in electrical engineering, right? Seepage in groundwater engineering, whatever, all that. Or it could be radians or intensity in atmospheric science. It could be ocean color in oceanography. I mean, it could be anything. Some quantity which is measured in any field, that is Y. X is that quantity which is causing the Y, which you believe X causes that Y. X need not be just X. It could be X1, X2, X3, multiple causes. So multiple parameters. So multi-parameter estimation, Y could also be several quantities. Okay. So, but usually we take a vector of temperature, or a vector of heat flux and so on. X could be emissivity, thermal conductivity, absorptivity, whatever. Okay. But if these parameters are correlated, okay, that means if there is a relationship between the heat transfer coefficient and the fin parameter in a fin problem, you can't get the answer properly. So you should figure out first using covariance. You should be good in mathematics and statistics. So you should figure out the covariance between various parameters and figure out that there is no cross correlation between the independent parameters. So first you have to establish which are the truly independent parameters. This is often a sore thumb in engineering. So how to figure out whether something is truly independent? So I don't know. So two ways of doing it could be probably you write down the equation and put it in dimensionless form. Then you will get some dimensionless numbers. So those dimensionless groups are the truly independent group. This is one way of looking at it if you have a forward model. Okay. If you are purely a data scientist, how you do it, I don't know. Okay. The other way of doing it would be take the dimensions, okay, of the dependent and independent quantity, m to the power of 0, l to the power of 1, t to the power of -1 and all that. You equate all the powers and then find out the dimensionless group. This is called the Buckingham pi theorem. So either by non-dimensionalizing the original equation or by using the Buckingham pi theorem, if you don't have a forward model, if you have Buckingham pi theorem, you can find out what are these dimensionless groups. Then even when if you're a data scientist, you collect all your dependent and independent variables in the form of these dimensionless groups and correlate the dependent dimensionless groups with the independent dimensionless groups. Is it okay? Dimensionless temperature is correlating as fin parameter, ratio of the temperature, ratio of something like that. Okay. So just because you have data, just like if there is a buffet meal, the idea is not to eat all the things, then you'll be down. Different people will like different things. You may be smart, you can taste many things, but whatever you like, you will eat more. That is the idea of a buffet meal. The idea of a buffet meal is not to eat everything, which is everybody, no person can eat all the items, okay? Even if you want, even if he or she want. So like that, you should pick and choose. So you should be smart. Like undigested, otherwise, just like the buffet meal causes you indigestion. You just take all the data and play like a Don Quixote who fought the windmill, and then you got your R code, Python code, bang, 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 and you just start processing the data. That will be like sheer madness. So if you are smart, if you do the background work homework before, you will be a smart data scientist. So how do we get smart data scientist? You should have the domain knowledge. Okay, you should know what the forward model is, or you should know what are the factors which are causing this. What is the physics behind this? Okay, that is very important. Okay, so if you come to Bayesian, the hallmark of the Bayesian is the use of prior. The prior can be two things. Objective is the P of X is 1. It doesn't matter. It's like bliss. I don't give any preference to any thermal conductivity. I want to find out thermal conductivity from temperature in a slab, but I don't give any preference. P of X equal to 1. You be done with it. But now left side, I know it is a metal. It looks like steel. Maybe the peak could be around 15 or 20. Then if you put the peak of P of X as 15 and a standard deviation of 10% of that, then you're putting in useful subjective informative prior. For a very loose prior, the P of Y of X will wash away the effect of prior. Suppose right side, if you give P of X equal to 1, the posterior and the PPDF and the likelihood, that is P of XY and P of Y of X will be the same. However, for a tight prior, the P of X and the P of X of Y will be very close. Therefore, it is a double-edged sword. It means what? Which is a double-edged sword? The prior. So the hallmark of the Bayesian is prior. Use your smartness. You use your smartness to get the prior. Okay, steps involved in solving a problem in the Bayesian approach. First, collect the temperatures, data collection to get all the temperatures. Model the likelihood, forward model, or if you have a neural network, have a surrogate model, neural network model. Model the prior based on your engineering experience, intuition, whatever. Construct the posterior. Okay. Then, same, assuming a Gaussian for the error, P of Y of X is like this, 1 by root 2 pi sigma square e to the power minus kappa square by 2. Kappa square is basically a difference between the measurements and the simulation whole square by sigma square, sum over all the measurements. Okay, after calculating P of XY, we need to get point estimates. Two estimates are massively popular. MAP, maximum A posterior A, that is the maximum in the curve, which I have shown. The corresponding X is MAP or the mean of the expectation. With no prior, the X bar will turn out to be like this, and the standard deviation can be found out. I'll give this presentation. This is too busy. I don't have to discuss all this formula. Easy to derive. If P of X of Y is evaluated only at discrete point, then the X bar equal to, please note that it will be sigma xi e to the power of minus chi square, no prior. Now it is chi square plus x minus mu p by 2 sigma square. That is, mu p and sigma p are the mean and the standard deviation of the prior. Suppose your sample xi is mu p itself, then the second term will be 0 on that e to the power of minus. So you will get the highest probability if your sample is the mean of the prior. If the sample is away from the mean, even though e to the power of minus kappa square by kappa I square by 2 is small, you will be penalized if you go far away from the mean. So the prior will influence your X bar. You understand? Can somebody endorse what? Did you catch what I told you now?
Yes, sir. We did.
So this is very nuanced, very subtle, but this is the hallmark of the Bayesian. Okay, and the standard deviation is one more second moment that is given like this. So this is a classic problem. I don't know whether we solved in the class on the quiz. There are 5 temperatures. Left side there is a Q. Thermal conductivity is 44.5. Standard deviation of the measurements plus or minus 0.3 degrees centigrade. Assuming uniform prior, 5 temperatures are given. So what we do now is sample. generate sample. What do you mean with generate sample? I want to find out Q 1300, 1700, whatever. Forward model is T equal to 35.3 minus Qx by K. Simulate the 5 temperatures. Experimental 5 temperatures are given. Get the difference. Square them. Add them. Divided by sigma square. Sigma is given to be 0.3. So that will give you your chi-squares. Okay. Then find out e to the power of minus chi-square by 2. Qi e to the power of minus chi-square by 2. Then get the PPDF. Now you can see that the mean is about 2258. The standard deviation is about 102. Standard deviation to mean should be about 5 to 10%, 5%, so that it's a reasonable answer. If you look at the left side, 1300, 1500, the PPDF, you can see the right side, whatever is indicated in red shows the highest PPDF of 0.7. Therefore, if you look at map, the map to this problem is 2300 watts per meter square. The mean to the problem is 2258. They are very close. So generally, I would prefer mean. Sometimes it's also good to check how close the mean and the map are. Okay. The online or the MHM. MH is Metropolis Hastings. MCMC is Markov chain Monte Carlo. Markov chain Monte Carlo means the next sample is dependent only on the previous sample. The Metropolis Hastings algorithm means whether the new sample will be accepted or not. Means we accept straight away, but we reject with the probability. Okay. So you generate a random number 1, calculate the next sample. The next sample can come basically based on a uniform distribution or a Gaussian, which is given in the bottom. Okay. Then first random number, based on the first random number, generate on random number. Then based on that random number, equate it to P new. Then get the new, so you please get the new X. And then if the second random is more than 0.5, the new sample is old sample plus sigma into U1. If it is less than 0.5, it is minus. Then you calculate the acceptance ratio, minimum of 1, P new by P old. If A is greater than U2, accept the sample, else you go back. What we are saying is, even though when you are going to a new sample, the P of X given Y, the PPDF is lower than the first sample, you don't reject straight away, you reject with the probability so that you don't get trapped in the local minima. This is the idea of the Metropolis. Then this is a fin problem from bottom to top. There are 4 temperatures. This is a long fin, theta by theta by e to the power of minus mx. We gave some temperatures. Iteration 1, first 3 random numbers. Somebody wrote a desperate. Okay, so this is how we proceed. Okay, so these are the various iterations. All right. Okay, so finally the fin parameter. So each of the samples you get the MPPDF and then you'll be able to get the map. Okay, so machine learning, the use of machine learning in inverse heat transfer. You also learned about ANNs, the very promising technique of physics-informed neural networks. Surrogate models like the above can be combined with inverse model to obtain expedited or fast retrievals of properties, fluxes, heat transfer coefficients, and so on. The ANN can also be completely data-driven without a forward model or differential equation. Professor S. Balaji would have taught you, without a forward model, an inverse techniques taught in the course can still be used. In this case, for example, historical data may be used to develop the ANN and current data can be used in the inverse solution. Okay, so the concluding remarks. So the objective of this course was to give the students an overview of inverse problems in heat transfer. Hello, who is that? Okay. To give the students an overview of inverse problems in heat transfer. So to give the students an overview of inverse problems in heat transfer and ways and means of formulating them. So I indicated and I quickly taught you about, I assumed that this is what you learned in the S. Balaji's questions. Okay. So the objective of the course was to give the students an overview of inverse problems in heat transfer and ways of formulating and solving them through examples. Of course, we have ensured that each of these examples can be done through hand calculation. That is my style. So this is our style. So once you learn this, then you can do big problems. Okay. So the rigor is very important. It is our hope that we are able to fulfill this objective largely, though we have to employ online teaching. And all of us were forced to adapt to the violent torrent of change. No? All of us have been subjected to boundless inconveniences. At least one family member or a close relative, somebody is suffered or suffering, or maybe there is also a death and all that. So we are really going through very bad times. Thank you for the cooperation. I think we maintained an average of 50, and till last week we had 70 students in the class, all the classes, which is very good. Okay. Sir? Now I stopped sharing. So anybody wants to, any comments, any questions, anything you want to ask, we have 5 minutes.
So can you please show that slide once in the Bayesian inference, the second slide?
I don't know what you're asking. I've closed that.
Hello, can you hear me, sir?
Yeah. 1 second, wait. I just closed the presentation. Yeah, which slide? Tell me, which is that?
So the Bayesian part, the second slide, I think.
I don't know what second slide. You tell me the title of the slide or something.
Sir, where we are finding the likelihood function for in the Bayesian.
Yeah. This one.
Sir, next slide. Sir, one more. One more, sir. Yes, sir. Sir, in this case, when we are finding the value of p of y given x in the left hand side, so for our case, this is the value of p of ti given q, right? For the example.
Not problem. Not ti. This t 1, 2, 3, 4, 5, 6.
Yes, sir. So t1 given q. Now, in that case, this is similar to finding the likelihood function that we have done in the maximum likelihood estimate, right? When we are calculating the value. Correct.
Tell me, what is the point? I understand everything. What is your question?
So the question is, in the first factor, 1 by √2 sigma square, should it not be whole to the power n, where we are making n number of readings?
Yeah. So that should be n. So if there is a sigma, there should be n. That is correct. Okay. So this, if you are doing a sigma j equal to 1 to n, there should be 1 by √2. Yeah, that's correct. Yeah.
Okay.
That is correct. But this I must have told in the class. In the class notes, it will be clear.
Sir, in the presentation also, like the same thing is like the mistake is.
Forget the presentation. What I wrote on the board, that is more important.
I will check.
What I wrote on the board, we have solved a problem. We couldn't have got the answer if you made such a serious mistake, right? No, just look at please always look at my work on the board. Slides, because I'm asking the TES to make, there can be some mistakes. Is it okay?
Yes.
Because when I do it chalk and whatever I write on the board finally, and we are solving a problem, if n is, then we will not get the correct answer. Is it okay? All right. So that is P, but please note that this will be only for one sample. Is that okay? Q1. Agreed?
Yes, sir.
Like that you will do for Q2, Q3. That n is not the nth sample. That n is the number of measurements. Is that okay?
Yes, sir.
That's okay. N is the number of measurements. Then you will do. So that's why I said one could be m, one could be n. So you have to be there are two counters. One is the number of measurements in each sample, and then the sample itself. Any other doubt? Any general feedback? So now I'm going to wind up. Thank you very much.